Jupiter's magnetic field is unlike anything we've seen in our solar system. The northern hemisphere's field sprouts wildly like weeds, while the southern field plunges back into the planet in a completely different pattern. This bizarre magnetic asymmetry has left scientists puzzled since Juno's 2016 discovery. Like unruly vines that reveal unexpected forces beneath the soil, these chaotic patterns suggest something extraordinary happening inside the gas giant. What mechanism allows Jupiter to maintain such a complex, lopsided magnetic configuration? The answer remains elusive, but its implications could fundamentally reshape our theories of planetary formation throughout the cosmos. This magnetic mystery may hold clues to processes we've never before considered and how worlds like ours come to be. The limitations of past Jupiter missions. For over 30 years, scientists have sent spacecraft to study Jupiter, yet these missions have only managed to document a fraction of the gas giant's complex systems. Our knowledge of Jupiter has evolved through successive missions, each revealing new aspects of this massive planet, but significant gaps in our understanding remained until recently. The Galileo mission, launched in 1989, represented our first dedicated attempt to study Jupiter extensively. After arriving at Jupiter in 1995, the spacecraft spent 8 years orbiting the planet, capturing images and collecting data that transformed our initial understanding of the Jovian system. Galileo confirmed the existence of a liquid ocean beneath the icy crust of Europa and observed the intense volcanic activity on Io. The mission also delivered an atmospheric probe that plunged into Jupiter's clouds, providing our first direct measurements of the upper atmosphere's composition. Despite these achievements, Galileo's design created substantial limitations. The spacecraft followed an equatorial orbit that kept it far from Jupiter's poles, leaving these regions completely unexplored, akin to studying Earth while never observing the Arctic or Antarctic. This orbital configuration meant scientists could only view a narrow band of the planet, missing crucial atmospheric dynamics occurring at higher latitudes. Additionally, Galileo's instruments can only capture the uppermost cloud layers, essentially seeing only the cover of Jupiter's complex atmospheric book without reading any of the pages beneath. When the mission ended in 2003, scientists had collected beautiful images of the colorful bands and the Great Red Spot, but gained little insight about the structures lying even 50 kilometers below this visible shell. Technical constraints forced Galileo to maintain a safe distance from Jupiter's intense radiation environment, which prevented precise measurements of the planet's magnetic field. During one close approach in November 2002, radiation levels overwhelmed the spacecraft's shielding, causing temporary instrument failures and corrupting nearly 75% of the data collected. This radiation hazard, the most intense in our solar system, created a frustrating paradox. The closer Galileo needed to approach for better measurements, the more likely it would suffer critical damage. The fragmented data from Galileo and earlier Voyager flybys left scientists with fundamental questions unanswered. How could Jupiter's Great Red Spot persist for centuries when similar Earth storms dissipate within weeks? Why did Jupiter's upper atmosphere measure nearly 600 degrees Celsius when theoretical models predicted temperatures below 200 degrees Celsius? The planet's water content, crucial for understanding its formation, remained unmeasured below the cloud tops where most water existed. These gaps were particularly frustrating because Jupiter's formation history holds keys to understanding our entire solar system's development. Jupiter's atmospheric patterns particularly challenged scientific models because they displayed unexpected stability. The distinct bands maintained their structure for decades, despite turbulent fluid dynamics that should disrupt them. Computer simulations consistently failed to reproduce these stable patterns without introducing special conditions that lacked observational support. With Galileo's limited view, comparable to trying to understand ocean currents by only observing surface waves, scientists couldn't determine what mechanisms maintain these enduring atmospheric structures. NASA recognized these scientific gaps and began developing a mission specifically designed to answer these open questions. The Juno mission would take a radically different approach, flying closer to Jupiter than any previous spacecraft. and following a polar orbit to observe regions Galileo never saw. The spacecraft would carry instruments capable of peering hundreds of kilometers below Jupiter's cloud tops to finally read the pages of Jupiter's atmospheric book, measuring its gravity field, magnetic field, and deep structure with unprecedented precision. Engineers designed Juno with a radiation-hardened vault to protect its sensitive electronics, a titanium box with walls over 1 centimeter thick, allowing the spacecraft to venture into regions where radiation levels would destroy conventional electronics within minutes. This innovative approach would enable Juno to make measurements from just 4,200 kilometers above Jupiter's cloud tops, compared to Galileo's closest approach of 261,000 kilometers. As NASA prepared for Juno's 2011 launch, the scientific community buzzed with anticipation. After decades of seeing only Jupiter's atmospheric facade, they would finally glimpse its inner workings. The mission promised to reveal the secrets of Jupiter's powerful magnetic field, 14 times stronger than Earth's, and mysteriously more complex than theory predicted. Scientists would finally determine whether Jupiter possessed a solid core, or if extreme pressures created exotic states of matter unlike anything we experience on Earth. The mysteries that had frustrated planetary scientists for generations were about to yield to new technology and a bold mission design. Juno would transform our understanding of gas giants from broad generalizations to detailed specifics, potentially forcing revisions to fundamental theories about planetary physics and formation. With each planned polar pass, Juno would collect data that might solve the puzzles previous missions couldn't address, revealing not just Jupiter's secrets, but perhaps also clues about our own planet's distant past and the mechanisms that shaped our entire solar system, engineering a mission to survive Jupiter. Designing a spacecraft to visit Jupiter presents a fundamental contradiction. Scientists need to get close to the planet to collect meaningful data, but proximity to Jupiter exposes the spacecraft to potentially fatal conditions. At its core, Jupiter creates one of the most hazardous environments in our solar system, particularly for electronic equipment. The planet produces radiation levels so extreme that conventional spacecraft components would fail within hours of close approach. The primary source of this danger comes from Jupiter's immense magnetic field, approximately 20,000 times stronger than Earth's. This powerful magnetic field traps high-energy particles from the solar wind, accelerating them to nearly the speed of light and creating radiation belts that encircle the planet. Any spacecraft entering these regions faces a continual bombardment by these particles, which can penetrate shielding and cause cascading failures in electronic systems. When NASA engineers began planning the Juno mission, they faced radiation exposure levels that exceeded any previous planetary mission. The radiation near Jupiter is approximately 10 times higher than the already dangerous levels around Europa, one of Jupiter's moons. This extreme environment would subject the spacecraft to the equivalent of 100 million dental X-rays over the course of its mission. Standard spacecraft electronics simply could not withstand this level of radiation exposure. The engineering team faced a particularly challenging problem because Juno's scientific objectives require getting exceptionally close to Jupiter, within just 2,200 miles of Jupiter's cloud tops. At such close range, the radiation exposure would be at its most intense, while previous missions like Galileo maintained much greater distances from Jupiter, limiting the precision of their measurements. This radiation created cascading engineering challenges throughout the spacecraft design. Solar panels are particularly vulnerable to radiation damage as high-energy particles gradually degrade solar cells. Computer systems face even greater risks as radiation can flip its memory, corrupt software, and permanently damage processors. Sensors and scientific instruments can produce false readings or fail entirely when exposed to intense radiation. Engineers needed to balance protection against practicality, finding the minimum shielding necessary while keeping the spacecraft light enough to launch and maneuver. Early design concepts with distributed shielding throughout the spacecraft proved inadequate against Jupiter's extreme conditions. Even specialized radiation-hardened electronics would be overwhelmed without additional protection. The mission science requirements complicated matters further. Juno needed to carry sensitive magnetometers that are particularly susceptible to radiation interference. The spacecraft also required precise attitude control systems that radiation could easily disrupt. Each scientific objective added another layer of complexity to the radiation protection problem. NASA engineers eventually developed a revolutionary solution: concentrate the most sensitive electronics in a single, heavily shielded compartment. This led to the creation of Juno's titanium radiation vault, a protective fortress about the size of an SUV's trunk. Weighing approximately 400 pounds, this structure became the centerpiece of Juno's radiation mitigation strategy. The vault's walls, made of titanium 1 centimeter thick, reduce incoming radiation by a factor of 800, creating a relatively safe environment for the spacecraft's most critical components. This approach represented a significant departure from previous spacecraft designs. Rather than trying to harden each component individually, the vault strategy protected the most vulnerable systems collectively. The spacecraft's main computer, power distribution units, and most instrument control electronics were all housed within this protective shell, allowing for more effective use of shielding material while maintaining reasonable spacecraft mass. For components that couldn't be placed inside the vault, engineers employed additional strategies. They used spot shielding for exposed but sensitive parts and incorporated radiation-tolerant materials throughout the spacecraft. Mission planners also developed software routines that could detect radiation-induced errors and restart affected systems when necessary. Juno's power system required particular innovation, becoming the first solar-powered spacecraft to operate at Jupiter's distance from the Sun, where sunlight is only 4% as strong as Earth. The spacecraft's 3 massive solar panels, each extending about 29.5 feet from the main body, were the largest ever deployed on a planetary probe at that time and served the dual purpose of providing power and helping stabilize the spacecraft. As a final protective measure, mission designers created an orbital path specifically to minimize radiation exposure. Juno would approach Jupiter over the poles, avoiding the most intense regions of the radiation belts concentrated around the planet's equator. The spacecraft would follow a highly elliptical orbit, coming close to Jupiter only briefly before swinging back out to safer distances, collecting essential data during each close approach while limiting cumulative radiation exposure. The solutions developed for Juno have established new standards for spacecraft operating in extreme environments. The titanium vault concept represents a significant advance in radiation protection strategy, with applications beyond the Juno mission, potentially enabling future exploration of other high radiation environments such as Europa or even closer studies of the Sun. After years of development and testing, Juno launched in August 2011, beginning its 5-year journey to Jupiter. The true test of these engineering solutions came in July 2016 when Juno finally arrived at Jupiter and began its close-range observations. The spacecraft's survival validated NASA's innovative approaches to overcome the seemingly impossible challenge of studying Jupiter up close, allowing Juno to collect unprecedented data about the gas giant while managing the severe radiation environment that had kept previous missions at a safe distance. Juno's revolutionary orbit. Juno's approach to Jupiter required a completely new orbital strategy. No spacecraft had ever attempted such a daring flight path, taking Juno just 4,200 kilometers above Jupiter's swirling cloud tops. This distance is remarkable when you consider that Jupiter's radius is about 70,000 kilometers. At its closest approach, Juno passes closer to Jupiter than the International Space Station orbits above Earth. The mission's scientific objectives directly shape this unique orbital design. To accurately map Jupiter's gravitational field, measure its magnetic properties, and analyze its atmosphere, Juno needed to collect data from extremely close range. Previous missions maintained safer distances from Jupiter, which limited the precision of their measurements. The Galileo mission operated at much greater distances to protect its instruments from radiation damage. Juno's science team determined that only by flying directly through Jupiter's gravity and magnetic fields could they collect the detailed measurements needed to understand the planet's internal structure. This proximity created a fundamental tension between scientific needs and spacecraft safety. Flying close to Jupiter exposed Juno to intense radiation that could damage its systems, yet maintaining a safer distance would compromise the mission's scientific goals. The team developed an orbital strategy that balanced these competing demands. The solution emerged as an elongated, elliptical orbit. Mission planners designed a path that would bring Juno extremely close to Jupiter for brief periods before sending it back out to safer distances. This approach limited the spacecraft's time in the most dangerous radiation zones while still allowing it to collect critical data during each close approach. The 53-day orbital period meant Juno would spend most of its time far from Jupiter, where radiation levels are significantly lower, then dive back for short, intense observation periods. This orbit provided a revolutionary scientific perspective. By approaching Jupiter over its poles rather than around its equator, Juno became the first spacecraft to directly observe Jupiter's polar regions. Previous missions followed equatorial or low-inclination orbits that couldn't view the poles effectively. Juno's polar orbit allowed it to see areas of Jupiter that had remained hidden from human observation throughout history, essentially diving into uncharted territory with each approach. Establishing this precise orbit required meticulous calculation and timing. During its approach to Jupiter on July 4, 2016, Juno had to fire its main engine at exactly the right moment to be captured by Jupiter's gravity. This Jupiter orbit insertion maneuver was entirely autonomous due to the 48-minute communication delay with Earth. The spacecraft had to turn away from the Sun, orient itself correctly, stabilize rotation, and ignite its engine without direct human control. The burn lasted 2,102 seconds and slowed Juno by 542 meters per second, placing it into its initial capture orbit. The success of this maneuver was crucial. It established the foundation for all future scientific observations. Each 53-day orbit creates a predictable rhythm to Juno's mission. The spacecraft begins far from Jupiter, gradually accelerating as Jupiter's gravity pulls it inward. As Juno approaches, it activates its instruments and begins collecting data. The spacecraft reaches maximum velocity during its closest approach, or perihove, when it's flying just thousands of kilometers above Jupiter's clouds at speeds exceeding 200,000 kilometers per hour. After this intensely productive period, Juno swings back out to its maximum distance of about 8 million kilometers. Originally, mission planners intended to reduce this orbit to a shorter 14-day orbit after initial observations. However, concerns about the main engine's valves led to maintaining the 53-day orbit throughout the primary mission. This choice extended the timeline, but created unexpected scientific opportunities, allowing Juno to explore regions dominated by Jupiter's magnetic field more extensively. Maintaining this orbit presents significant challenges. Jupiter's massive size creates a complex gravitational field that can gradually alter Juno's trajectory. The spacecraft must perform periodic adjustments using its thrusters to maintain the desired flight path. Additionally, the extreme radiation environment can affect the spacecraft's systems, requiring constant monitoring from mission controllers. Each close approach represents both risk and extraordinary scientific opportunity. During these periods, Juno flies through radiation levels that would quickly damage unprotected electronics. Despite its titanium radiation vault, Juno has experienced several safe mode events during close passes. These events trigger automatic shutdown of non-essential systems to protect the spacecraft. However, each perihove also provides unprecedented data collection opportunities, with instruments measuring magnetic fields, gravitational variations, and atmospheric composition with remarkable precision. The scientific payoff from this orbital strategy has been remarkable. Juno's close-range observations have shown that Jupiter's weather systems extend to depths of about 3,000 kilometers. The mission discovered that Jupiter's magnetic field is significantly more complex than earlier models suggested, with unusual concentrations in the northern hemisphere. Most significantly, Juno's orbit provided humanity's first direct observations of Jupiter's poles. When Juno's cameras finally captured these regions, they revealed structures unlike anything seen elsewhere in the solar system. Instead of patterns similar to Saturn's hexagon, Juno discovered clusters of massive cyclones arranged in geometric formations. In the north, 8 cyclones surround a central storm, while the South Pole hosts 5 similarly arranged cyclones. The success of Juno's orbital strategy has led to the mission's extension through 2025, allowing additional orbits and expanded observations of Jupiter's ring system and moons. Each orbit continues to provide new data, gradually building a more complete picture of Jupiter's complex systems. The surprise at Jupiter's poles. Before Juno, scientists had never directly observed Jupiter's poles. Earth-based telescopes could only view the planet's equatorial regions effectively, while previous spacecraft missions followed orbital paths that kept them near Jupiter's equator. This left Jupiter's poles as mysterious territories, visible only at oblique angles that revealed little detail about their structure or dynamics. Scientists made reasonable assumptions about what they might find based on observations of Saturn, the other large gas giant in our solar system. Saturn's North Pole features a striking hexagonal cloud pattern, discovered by the Voyager mission and later studied in detail by the Cassini spacecraft. This hexagon, a wave-like jet stream that flows around the pole at about 200 miles per hour, has maintained its six-sided shape for decades. Given the similarities between Saturn and Jupiter, many scientists anticipated Jupiter might display comparable geometric features at its poles. As Juno approached Jupiter in 2016 and prepared for its first polar pass, the scientific team eagerly anticipated their first clear view of these unexplored regions. Would Jupiter's poles mirror Saturn's organized structure, or would they simply show extensions of the familiar banded patterns seen at lower latitudes? The team prepared their hypotheses, ready to interpret what they expected would be variations on familiar planetary atmospheric patterns. When Juno's first images of Jupiter's poles arrived back on Earth, the scientific team was stunned. "We were wrong about everything," admitted one Juno mission scientist during an early press conference. Juno revealed something entirely unexpected. Clusters of massive cyclonic storms arranged in surprisingly organized formations around each pole. At the North Pole, Juno observed a central cyclone surrounded by 8 additional cyclones, all arranged in a remarkably regular octagonal pattern. Each of these storms measures approximately 2,500 miles across, roughly the distance from New York to Los Angeles. A single Jovian cyclone could cover most of the continental United States. Their spiral arms visibly touch neighboring storms, yet they maintain their individual identities and positions. Jupiter's South Pole showed a similar but distinct arrangement, 5 cyclones surrounding a central storm in a pentagonal pattern. Later observations revealed a 6th cyclone had somehow muscled in on this arrangement, creating an even more complex configuration. The sizes of these southern storms are equally massive, with diameters comparable to their northern counterparts. These cyclones represent atmospheric structures unlike anything seen elsewhere in our solar system. Wind speeds in these massive storms have been measured at over 220 miles per hour, stronger than the most intense Category 5 hurricanes on Earth. Perhaps more surprising than their existence is the stability of these cyclonic formations. On Earth, when hurricanes approach each other, they typically interact in a process called the Fujiwara affect, where they orbit each other and eventually merge or disperse. The Jovian polar cyclones, despite their spiral arms touching, have maintained their positions and individual structures for years. This stability presents a significant scientific mystery. According to conventional fluid dynamics, these tightly packed vortices should interact, merge, or repel each other. Yet they remain locked in their geometric arrangements over extended periods. Scientists have begun developing new models to explain how these massive cyclones maintain their positions without combining into a single giant storm. One emerging theory suggests that the cyclones are kept separate by smaller anticyclonic storms positioned between them. These smaller storms may act as barriers, preventing the larger cyclones from merging. Another hypothesis proposes that deeper atmospheric layers beneath the visible clouds provide stabilizing forces that maintain the cyclone's positions. Juno's thermal infrared imaging added another layer to the mystery. Temperature mapping revealed the cores of these cyclones registering as surprisingly warm compared to surrounding areas. This temperature difference suggests these storms extend deep into Jupiter's atmosphere, potentially connecting to heat sources far below visible cloud layers. The infrared data also showed sharp temperature boundaries between the cyclones and surrounding regions, indicating these storms effectively trap heat within their circulation patterns. These temperature gradients may contribute to the storm's stability, creating energy barriers that prevent them from merging with neighboring cyclones. Color differences visible in Juno's images provide additional clues about the composition of these polar storms. The cyclones appear bluish compared to Jupiter's typical tan and orange cloud bands, suggesting different chemical compositions or cloud heights in these regions. The blue coloration likely indicates clouds at higher altitudes where temperatures are colder. What makes Jupiter's poles truly unique in our solar system is this combination of features.